7 less than 1. So guys, if you're on Moodle and stuff and you do open stuff for me, I'm in the process of updating everything, so all the numbers are changed. This used to be used to be unit 6 because I broke 4 into 2 units, and then I added one. I also put this one before trig. I usually do this one last. So just a little bit of switching around. But the point is, everything's in the right section for Moodle. If there's any labeling issues, sequence and series is our unit 7. Okay, so just keep that in mind if there's any like things you're confused about when you open Moodle up. Okay, because like all my my videos, I believe are units. They say it's unit 6 that are made. That's why we're remaking them now. So, all right. So in this unit, we're going to investigate patterns to find 2 types of sequences: arithmetic and geometric. We derive rules from the general term to each sequence. So what's confusing about sequences and series is that everybody gets upset about the general term. If the general term is the term which represents the pattern. So that means like I could say this is the pattern, it's created by this in a general term sense. So what that means is that you could tell me, I could say, well, what's this pattern? You'd be like, well, it's going up by 3 every time. Okay, good. Now write that in general term. Oh, n plus 3. So I'm adding 3 every time to whatever spot I'm at for term number. Okay, so the confusing part gets the general term piece. A lot of you guys know how to identify patterns and look at different patterns, but we'll get to that stuff as we go. Okay, just give you the short summary. Arithmetic is adding, subtracting patterns. Geometric's multiplying. Okay, we say always multiplying, but if you're multiplying by a half, you're dividing by 2, right? But always multiplying, okay? Okay, so let's look at investigation 1 here. Jesse's making a tower using playing cards. The top 3 rows of the tower are shown. You got row 1, row 2, row 3. So then how many cards are required to make these? So if you think about it, you're just pretty much counting the lines. So the top row, you have 1, whoops. We have 1, 2, 3. Okay, row 2, change color so we can see it. 1, 2, 3, 4, 5, 6. We don't count that top card again. And the third row, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we get an idea that the pattern is growing by 3. Okay, let's switch our way of thinking. We were just counting the cards there. Now let's think about just the triangles that are there. So the very first row, there's just 1 triangle. When you add the second row, you're adding 3 triangles. The third row, 1, 2, 3, 4, 5 triangles. So you can see this is going by 2 every time. Okay, pretty straightforward. All right, still ask questions. Okay, investigation 2. I don't know why that's highlighted. It's interesting. Okay, each row of triangle is named after. So if you're wondering, like, what we're doing, we're going to build all these different patterns, and then we're going to identify them later. So we're leaving that. We're coming back to it. So now we're looking at a different one now. Each row of the triangle named after a French mathematician named Blaise Pascal. It's Pascal's triangle. Begins and ends with numbers 1s. Okay, so apart from the ones everywhere number, every other number in particular row can be determined by adding the 2 numbers diagonally above it. So, for example, if I want to know how I got 3, 2 plus 1 diagonally. Okay, that's how it's built. Okay, so like the 2 here is kind of like a little bit unique because it's you also can do it like this as well. Those 2. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 2 is 3. And then people are always like, why is that a 1 on the outside? Well, because it's technically 1 plus 0. There's nothing out here. So that's how it's built in terms of the pattern for Pascal's triangle. Okay. All right. So sum the number of numbers in row 1. So row 1, it's a 1. 1 plus 1 is 2. 1 plus 2 plus 1 is 4. 3, that's 8 for row 4. 16, good. You're really good, good job. Okay, so it's doubling every time, good. You know, if we just look at this here, just so you can see, it's a 1, that's 4, that's 6, that's 4, that's 1. Okay, if I wanted, I'll do one more row here. So that's 1, that's 5, that's 10, that's 10, that's 5, that's 1. And it just keeps going further and further like that. So just to confirm, guys, 10, 20, 30, 32, row 6, 32. Okay, a couple more patterns we're going to look at here. So this one's a little interesting too. Investigation, an equilateral triangle 1 has sides of length 32. A smaller triangle 2 is placed inside of triangle 1 by joining the midpoints of triangle 1. It's illustrated in diagram 2. The patterns continue in diagram 3. Diagrams 4 and 5 in the sequence have not been completed. Complete them. So we're going to do 4 and 5. So you got to get a little bit small for number 5. But so what you're going to do is you're going to draw a midpoint here. You're going to connect and make a new triangle. It's going to be really hard for me to do with mine. Let's see if I make my pen a little bit thinner. Might be able to do it on this one. So then we do here. Let's do it again. Midpoint, midpoint, midpoint. So I got it in there. Okay. Then you're going to use that for reference. I'm going to lose this picture, but use that for reference when we fill out the table about how many triangles are in the pattern. Now, when you think about that, so this one's simple. It's one triangle, right? But check this out. This one's 1, 2, 3, 4, 5 for the big one. So that one has 5 triangles. Okay? So like this one has 1, 2, 3, 4, 5, 6, 7, 8, 9. So length of side of the triangle. So we know the lengths of the side and the inside are just getting halved every time. 16, 8, 4, 2. Then it went 1, 5, 9 for 3. Who can give me how many triangles are in 4? 13? 15? Okay, let's count them here real quick. So remember, this one, we're going to draw this one. We can do this one real quick. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay? Sorry. Got to make sure you count the the center one. Oops, sorry. That was 9, then 13. So then you're kind of seeing the pattern, though. It goes 9, 13. So then what do you think this one is? 17. It's adding 4 every time. It's adding 4 triangles every time you do that move. Okay? Okay, now we're going to do investigation 4. The mean daily temperature in Calgary on January 1st was 8 degrees Celsius. For the next 10 days, the mean daily temperature decreased by 4 degrees Celsius each day. Complete the table below. Just the idea that you can go into negative with some patterns. Some things make sense to have negative, like temperature. Okay, so here we go. Now we're going to kind of summarize. Oh, we got 2 more, sorry. They're summarized. So each of the following tables, A through F, the top row consists of natural numbers, 1, 2, 3, 4. So that's like your term number. We're going to talk about that more some later. And the bottom row consists of the sequence or the pattern that's related to that table or situation. So in each of the following, so we're going to look at all these tables now. So complete all the tables from previous. So let's have you guys help me here. So let's do the first 4. Let's do A, B, C, D. So these are the ones we already filled out. So Lucas, can you help me fill out A again? So what was A? Okay, 9, 12, 15. And then so the next term can be calculated by, what are we doing? Adding 3 to the previous term. So plus 3, but add 3. Okay, what is term 6? 18. Term 7, 21. That's what T means. T of 6, term number in the pattern. Okay. Next term can be calculated by, so what was table B doing? What is table B doing? Joel, what do we have down for table B? Just turn back a page, the ones we filled out. If you don't mind reminding us. 13579. So next term can be calculated by plus 2 to the previous term. So term 6, 11, term 7, 13. Okay, good. Emily, what was table C? What do we have for table C?
1, 2, 4, 8, 16, 3, 6, 4.
Okay, next term can be calculated by? Right, so doubling the previous. No, because n, what's 2 times 3? Yeah, so yeah, you're on the right idea. Okay, doubling previous term. We're going to learn how to write that. Okay, doubling previous term. T8, so it's 128 and 256. Thank you. Okay, what about table D? What do we have for table D? Go ahead, Britton. 32, 16, 8, 4, and 2. So this one we were what? Halving the previous term, yes. So then it's going to be 1 and then 1/2, right? Half of 2 is 1, half of 1 is 1/2. Okay. And last two tables we had, table E. Riley, what's table E? What was that one? 1, 5, 9. Okay. So the next term can be calculated by, right, added 4 previous term, so then 21 and 25. Okay, and Abby, what was table F? 8, 4, 0, -4, -8. Okay, so next term we calculated by subtracting 4 to the previous term, -4. Right there is fine. Right, -12, -16. Okay. So we're going to identify what types of sequences these are. Okay. So as I told you at the beginning, arithmetic goes with addition, subtraction. So all the ones that you're adding, subtracting those patterns, those are arithmetic sequences. All the ones that we're multiplying in some way, those are geometric. So we just established those are two things we're going to do. So guys, this unit goes like this. We're doing a little intro now. 2 and 3 are arithmetic. 4 and 5 are geometric, and lessons 6 and 7 are infinite. We talk about infinite series. Okay, so that's what we're breaking this down to. Right. And I always say, even for adding, just say always adding, we're adding a negative. And then multiplying, always say multiplying if you're dividing, just multiplying by 1/2. That makes it keep it simple, so you're only using 2 operations. You can say I'm always adding or I'm always multiplying. So you don't have to worry about divide or subtract. Okay. So anyway, I just summarized this. Other sequences are just sequences that don't really have a pattern. So if they don't have a consistent add or a consistent multiply, then they're going to be an other. Okay, they're a sequence with no pattern essentially. Okay, so for example, prime numbers. If you listed your prime numbers, well, the pattern is their prime numbers, but they don't have anything in terms of adding, subtracting, multiplying, right? So that would be an other sequence. Okay, Fibonacci's 1, 1. So Fibonacci's is adding the previous 2 terms. 1 plus 1 is 2, 1 plus 2 is 3, etc. But that's not a consistent pattern. Okay, so that would also be an other. Okay. So here's your little quick little flow chart. Sequences, you got arithmetic, geometric, other. Okay, classify all of them. So let's just do, we have arithmetic, geometric, and other. Okay, so let's just go around A through F. So Hunter, what was A? What type of sequence? Okay, good. So A is in the arithmetic column. Okay, what was B, Parker? Arithmetic. C, Jared? Geometric. Okay, D. Alan, what do you think for D? D, is it arithmetic, geometric, or none? For the type of pattern that one D will. Let's see. Looking at this guy right here. Huh. So D, yeah, is it going half? Yeah, so geometric. Yep, it's halving every time. Okay, good. Gavin, how about E? Arithmetic. And F, Riley. Also arithmetic. Okay, good. Okay, so that was your patterns. We had 4 of the arithmetic and 2 were geometric. Okay, good. Now, finite versus infinite. Okay, so finite is countable, infinite is not countable because infinite goes forever. So when we're doing these like sequences, what we can do is if you see a number with a period, that means it stops. Doesn't keep going. That pattern stops there. If you see a pattern with 3 dots, that means it's infinite and keeps going. Okay? Simply, period means stop, finite, countable. 3 dots means infinite, doesn't stop. Okay, not countable. And it's not countable in the sense there's no limit. It keeps going forever. Okay. Any questions on that? Okay. Great, keep on going here. A sequence as a function. So we can write these as functions a lot of times. Like for example, something that's doubling every time is simply a line with a slope of 2, right? Because every time you like 2x plus 1, every x value it jumps up by how much? 2. So that's a pattern of 2, right? So just thinking about that idea that these can be related, some of them can be put in terms of functions. So when you think about adding, subtracting, that's going to be slope. So when you have a arithmetic, that's actually going to be a linear model. Okay, when you're multiplying, that's going to be more of a geometric model and more of a quadratic model because those are growing faster. Because think about how fast it goes. It goes 2 to 4 to 8 to 16 to 32, so it's taking off. So it's a little bit more of a curvature of an exponential look. Okay, so it's a little bit more rounded. Okay, we'll get to that though. So the domain and range is instead of all naturals, the range is just the terms in the sequence. So what are the possibilities? Okay, so table A, we're just going to, so we're going to do it real quick. We're going to plot the values from our graphs that we were doing. So table A, let me get mine here real quick. Let me pause the video. All right, so table A simply looks like this. It went at 0, 3, 0, 6, 0, 9, and 3, 9, 4, 12. And so you see it's got that linear model because there's arithmetic for table A. Table B was 1, 1, 2, 3, 3, 5, 4, 7. Again, linear there because arithmetic. Then you look at C. C is interesting. 1 was at, what, 2? Yeah, 2, 4, 8, 16, 32, 64. So you see how it takes off there of an exponential look. It's got curvature. Okay? So you're kind of making the connection right now, guys. It's arithmetic is a linear model. Geometric's an exponential model. Okay, I just applying the points that you guys had in those tables in the previous pages, okay? I'm just going to go ahead and keep going here. So then these 3, so table D. D was halving every time, so it went 32, then 2 was 16, 3 was 8, 4 was 4, 5 was 2. And so you see this one's curvature in a different direction. It's getting smaller. That's a decay exponential look. Okay, table E, the 1, 1, 2, 5, 3, 9, 4, 13, and 5, 17. Again, linear, because arithmetic. And then table F was the one with the degrees, and so that one started at 1 was 8, and then went to 4, went to 0, -4, -8. So you just have a nice little linear model going through the positive and negative pieces. Okay. All right, so we're almost done. Okay, last little page. Okay, so here's what we got. Says, circle the correct alternative to the following statements. A sequence in which the next term is determined by adding a constant to the previous term is arithmetic or geometric? Arithmetic, adding, right? Sequence can be represented by, so is arithmetic a linear or nonlinear? Linear, good. So that's all we're putting together today. A sequence in which the next term is determined by multiplying the previous term is geometric. The sequence can be represented by a linear or nonlinear function. Nonlinear, it's curved. Okay, that's it. Okay.